Welcome, airplane designers and aviation enthusiasts. You have found an ultralight airplane design video from the Ultralight Airplane Workshop. This is part 2.1 of a series of videos working on an ultralight airplane design that we are calling the UWS-4. But we're using a book from Dan Raymer called Simplified Aircraft Design for Homebuilders in order to guide us in our design. Although it's not a step-by-step design procedure, it is a pretty good guide for guiding first-time airplane designers or ultralight airplane designers through their design. There is a part 2 video, but after I made it, I decided it was a little bit confusing, so I decided to make this part 2.1 video, which is a little more streamlined and hopefully less confusing. So if you've already seen part 2 and you understood it perfectly, you could probably skip this video. If you have not seen part 2, this is probably the better video to look at. And what are we going to talk about in this video? We're going to talk about sizing, and sizing specifically for ultralights. One of the things that made part 2 a little confusing is Dan's method for determining the size of an airplane. In this case, he's really talking about the gross takeoff weight, is that it's really designed for light airplanes, where the pilot is not a major part of the weight of the airplane. And in fact, fuel can frequently be heavier than the pilot. But for ultralights, that's not the case. For ultralights, we have a very small amount of fuel. It's a small fraction compared to other light airplanes. And the pilot is a significant part of the gross weight, where it's not as significant for light airplanes. So we're going to change Dan's procedure just a little bit, not only because it's for a much lighter airplane, but also because we have some requirements for meeting the FAA Federal Aviation Regulation Part 103 requirements. And that pretty much sets the weights that Dan is trying to estimate for people who have no idea what some weights are going to be. So we can actually do some things a little bit simpler than Dan does. Before we get into it, I wanted to give a quick thank you to my patrons. At the designer level, we have Keith and Richard, who have been longtime patrons, and the newest patron, Shane. Now, I also want to give a quick thanks to the earlier bird patron, Ryan, who also recently became a patron. So I want to give a big thanks to you guys. Now, let's get to it. Let's review what we learned in the Part 1 video. In Part 1, we got introduced to Dan's book, Simplified Aircraft Design for Homebuilders. I wanted to emphasize that the videos that I'm doing on Dan's book are not a substitute for buying Dan's book. I'm leaving out a whole lot of information, in particular numbers and descriptions of other configurations that we're not doing in this particular design, but would be applicable to other designs. And by the way, if you want to buy this book, I'll put a link down in the description of this video where you can click on it and it will take you to Amazon. Then the channel will get a small cut of the proceeds of that book. Now back to talking about Part 1, we went over the goals, and that's something that Dan talked about. We went over requirements that Dan does not talk about, but I really think requirements should be part of your design process. And it's really important for us doing Part 103 designs because we have some weight requirements and some speed requirements that we really need to meet. Then we did 2 calculations that would be used in later videos. One is the power loading, and that's the number of pounds of the airplane. Oops. Now you may have noticed I just swapped these 2 numbers because I just realized I had them backwards. So let's get back to this. So we calculated power loading, and that turns out to be number of pounds of the airplane per horsepower. And we'll use that a little bit later when we're actually trying to figure out what engine sizing we should use on the airplane. And we also calculated wing loading. So it's going to be gross weight per surface area of the wing, so in square feet. And we're actually going to use this in this video. We also figured out how to calculate dynamic pressure. So that's pressure on the airplane that varies with speed. And we also figured out what the maximum coefficient of lift of our wing is going to be, or at least a value that we can use to keep the FAA happy. Now, as I said in the introduction, we're going to do sizing in this video, and that's figuring out what the gross takeoff weight of the airplane is. And we're going to simplify Dan's approach quite a bit, and we're going to vary one aspect of Dan's approach too. And the way we're going to do this is we're actually going to take advantage of being able to directly calculate some of the weights. And that allows us to bypass some of Dan's estimates and makes things simpler. So this C sub D0 is the coefficient of parasitic drag. And by the way, If you don't know what some of these aerodynamic terms I'm going to use are, I'll put a playlist up here in the upper right hand corner that you can click on, and somewhere in that playlist you'll probably find a video that covers the aerodynamic term that we're talking about. And I know there's definitely one for the drag. Now if you don't want to do a range calculation for your airplane, we could actually skip this whole page here. But we would probably want to use it a little bit later in some other calculations in future videos. So let's go ahead and calculate it here, just because Dan includes it in the sizing. Now Dan's equation for estimating, and it's a really rough estimation of the coefficient of parasitic drag, is to estimate the coefficient of friction drag and then multiply that by the ratio of the wetted area to the surface reference area of your airplane. Now this is a ratio. You don't have to know either one of these specifically. We just have to estimate the ratio of these two. Now let's go ahead and talk about what these two numbers are. The wetted area of the airplane is the surface area of the airplane that would be wet if you dumped it in water. So the surface reference is the surface area of your wing as you're looking at it from above. So this is a planform surface area. And it includes the area of the wing that's occupied by nacelles, pylons, and the fuselage. So you don't exclude those areas. Now Dan says we can estimate this ratio based on other airplanes that are similar to the one we're talking about. And he has a great table there. And he separates it by single engine and double engine and by the configuration. Now we're using a conventional configuration, which means we have a big wing up front and a small tail back behind. Now he also talks about other configurations like a canard configuration. But for a conventional configuration with a single engine, this ratio is 3.8. And what's nice about this ratio is it's pretty much independent of the overall size of your airplane. The dependency is more on the configuration and the number of engines you have. So it makes this number pretty nice because it'll apply to ultralights as well as large airplanes. Well, now let's talk about the coefficient of friction drag. And again, this is completely independent of the size of the airplane. It's more independent on how you've constructed the surface of the airplane and some of the aerodynamic choices you've made. And again, Raymer has a nice table. So he has various values depending on the number of engines and the aerodynamic cleanliness of the airplane. So an average home-built design cleanliness is what we're going for. But we also have clean designs, and by clean, Raymer means very aerodynamically clean. And in another example, he has a clean strut-based. But for our ultralight, we're going to use 0.009. Now, it would be nice if we had some more values for ultralights. For example, wire braced would be a nice value, which I'm guessing this is going to be a bigger number than 0.009. But our airplane is structurally going to be very similar to a lot of home builds. So this is an appropriate number for this particular design we're working on. So if we plug our values in, we got the 0.009 for the coefficient of friction drag. We got 3.8 for a ratio of wetted area to reference area. And this is our calculation. So our coefficient of parasitic drag is 0.0342. And we'll use that a little bit later. The next thing that Dan has us figure out is the drag due to lift factor. And this is a lot like that coefficient of parasitic drag that we just talked about. And by the way, this P.18 up here, that means page 18. So for example, back here on the coefficient of parasitic drag, that was page 17. So on page 18, we're doing drag due to lift. Now this 0.75 is the efficiency of the wing. So what Raymer is saying is you probably have no idea how efficient your wing is going to be at this point. So just for now, assume it's 75% efficient. And that's actually not too far from the efficiency of a lot of home-built airplane wings. So it's not a bad start. Now in the future, after we've designed our wing, maybe we can go through some analysis that shows that it's actually more efficient. So we might be able to get up to 80, and if we're really, really lucky or really, really good, we might be able to get up to 85% efficient. And by the way, a 100% efficient wing would have a 1 here. So as you can see from this drag value is inversely proportional to your aspect ratio. What that means is, as your aspect ratio increases, your drag decreases. So that means you would like to have a higher aspect ratio in order to reduce drag on your airplane. In order to have a high aspect ratio wing, you usually have to make some other sacrifices somewhere else in order to keep the weight low. Now what I'm going to do is I'm going to initially start with an aspect ratio of 4.5. And that's a fairly low aspect ratio. But there's a little bit of an issue with that. The higher your aspect ratio, in general, the heavier your wing is going to be. And that's why you see a majority of ultralight airplanes do not have a high aspect ratio wing. And let me put a link to a video up here in the upper right hand corner where I talked about how aspect ratio affects weight. So I'm going to start with 4.5, and what I will do is after I get through my initial analysis, if I have some weight to spare, in other words, I could have a little bit of room to make the airplane heavier, and we'll talk a little bit in a moment about why that might be difficult, then what I'll come back and do is increase this aspect ratio until I meet my weight limit on my airplane. And that will get me the lowest drag that I can get from the aspect ratio. So if we plug all of our values in here, we get 0.094 for our K factor. Now let's use that K factor, and let's use our parasitic drag coefficient. So the next thing to look at is our lift to drag ratio, and that's on page 18. So it basically tells us how far forward our airplane can fly for each unit that we lose in altitude if we're gliding. So the higher the aspect ratios, the farther we can glide. So let's do our calculation. Now this one's one of the more complicated equations that Dan has us do, although there are some really complicated ones a little bit later, but it's going to be a few weeks before we get to that. So Q is our dynamic pressure. Now we learned about that in our video on part 1. And in this case, I'm going to do Q for our cruise speed. So our cruise speed is 45 knots, and I'm just kind of pulling that out of thin air. Now I know it has to be lower than 55 knots according to our FAA regulations, and that's when you've got the power firewalled on your airplane. So I'm going to assume cruise is somewhere between 40 to 45, and for this calculation, let's call it 45 knots. Now this is the coefficient of parasitic drag that we just calculated. This is the wing loading estimation that we came up with in part 1. And this is, again, the same wing loading estimation. Here's the value K, the drag to lift factor that we just calculated. And again, the same Q we just had over here. Now, Dan has you multiply this wing loading by 0.98. And what he's trying to do is account for fuel that you're going to lose as you're climbing up to cruise altitude. This is supposed to be our lift to drag for cruise, and so we're going to lose a little bit of weight while we're climbing out, and so this 0.98 is supposed to account for that lost weight. So if we plug all these values in here, we get a lift to drag ratio of 8.78. Now that's not a horrible lift to drag. That essentially means that for every foot we lose in altitude when we're at our optimum glide ratio, that we can move forward about 9 feet, just a little bit less than 9 feet. So every drop in foot, 9 foot forward. This is not horrible, but it's not great either. I'd like to be up to around 10 at least if we could, and we might be able to reach that, but it will have to be in a later video after we have refined our design. Now here's where we can do a simplification of Dan's approach, and that is the percentage of your fuel that is part of your gross weight. Now Dan assumes that you have absolutely no idea what the gross weight of your airplane is going to be and no idea what your fuel weight is going to be for the airplane. And what he wants to do is come up with an estimation of your fuel fraction. But we really don't need to do that. And the reason for that is we have the FAA regulations, Part 103, and specifically Part 103.1E2. And it says that you cannot have a fuel capacity exceeding 5 US gallons. So you can go right up to and including 5 gallons on your fuel capacity. And we know that fuel weighs 6 pounds per gallon roughly. So the weight of our fuel is going to be 30 pounds at takeoff. So we basically already know how much our fuel is going to weigh because we want to get as much fuel on that airplane as we can to go cruising as long as we can. Dan's calculation to figure out this fuel fraction figure out the gross weight, and then multiply the fraction by the gross weight to get the fuel weight. We can short circuit all that and just go with 30 gallons. Now here's another weight that we can simplify much easier than using Dan's approach, and again, it's because of the FAA regulations. FAA regulations say that the empty weight of our airplane, and we'll talk about what that means in a moment, has to be less than 254 pounds. So you cannot equal it, you have to be less than. But let's go back and let's talk about what empty weight means. Empty weight means every permanent part of the airplane, in other words, parts that cannot be removed. So for example, you don't include fuel in the empty weight, you don't include the pilot, you don't include baggage, you don't include engine oil, you don't include coolant, so things like that. So once you remove all that stuff, that's the empty weight of your airplane. So what Dan does is he comes up with an empty weight fraction. So that's an estimate on the ratio of the empty weight to the gross weight of the airplane. You don't need to know either one exactly to start with, but he can come up with a ratio for that. And then later, you figure out what the gross weight of your airplane is, and then to figure out the empty weight, you multiply the gross weight by that ratio, and then you get the empty weight. But we don't need to do that. We got this 254 pound limit, so we know that our empty weight is not going to be more than that. But this 254 pounds does not include things like floats and safety devices. I forget what the value is you get for floats, but there's a maximum value of weight that you can have for floats. And there's a maximum value for safety devices. And for safety devices, that's 24 pounds. So you can have up to 24 pounds more added to this 254 for things like parachutes. And then we can also have a pretty good estimate on what the lower limit is. Now, if you go around and look at the empty weights on lots and lots of ultralights, you'll find out that a lot of them are between 240 and 254 pounds. There's very few that are actually lower than 240 pounds. And it's just difficult to design an airplane that can carry, let's say, a 200-pound pilot and still meet a 3-point-G load limit. It just takes a fair amount of material and structure to do that. So I'd estimate that you're going to have a very difficult design getting your ultralight airplane empty weight below 220 pounds. If you think you can get a lower weight on your airplane, then by all means, go ahead and use a lower empty weight. And an example of that might be you found a design where the empty weight is like 200 pounds, 210 pounds, something like that, and you just want to make some changes to it that you don't think are going to affect the empty weight. Then by all means, go ahead and use that 220 pounds or 210 pounds, whatever you got. But for this design, I know that for the aspect ratio, I'm going to keep cranking that up until I get this 254 pounds. Let me reword this. In future iterations of going through the design, I want to reduce that lift due to drag. In order to do that, I'm going to have to increase my aspect ratio. But increasing my aspect ratio is going to make the wing heavier, making my empty weight heavier. So I'm going to keep cranking up that aspect ratio until the weight of my airplane hits 244 pounds. Or I get up to a length of the aspect ratio where it starts to get unwieldy. Like, for example, I'm not going to crank up that aspect ratio until the span gets more than 30 feet. Beyond that, it starts to get to be a little bit unwieldy handle. And by that, I mean handling on the ground, loading it and unloading in a trailer, etc. So, for my airplane, we're going to use an empty weight of 254 pounds. Okay, so now we've almost figured out one of the main things that Dan's trying to figure out with all the estimations that he's done up to this point. It's trying to figure out the gross takeoff weight of the airplane. But we already know the empty weight. We already know the weight of our fuel. And we've got a few other things to figure out. For example, the pilot. So I'm designing this airplane for a 200-pound pilot. So that's about how much I weigh. If you were a 300-pound pilot, you'd stick 300 pounds in. I'm also going to include a soft pack parachute. That's 18 pounds. Now I could go up to 24 pounds, but I'm only going up to 18 because that's how much the soft pack parachute I looked at weighs. And I'm also going to include 15 pounds for extra stuff. Now I said back in the goals that I want this to be kind of a touring airplane or a plane to fly to local friends that have airports so I can go visit with them. So I'm going to take some extra stuff with me. For example, I'm going to take tools. In case I have some things that need to be changed, like changing spark plugs. changing tires, etc. I'm going to take tie downs because it's possible I'll have to stay overnight. So I don't want the airplane to blow away, so I'll take tie downs with me. I'll take a blanket with me just in case I have to sleep in the airplane overnight. I'll take water and snacks for while I'm flying. I'm going to take maps because I'm actually going to go on fairly long distances over territory I may not be familiar with. I'll take a backup GPS and I'll take my cell phone. So I'm going to include all that in baggage, so I'm going to design it to have another 15 pounds. So if I add all that up together, I'm getting 517 pounds. So that's what I'm going to use for my gross takeoff weight. Now, for your own design, of course, you're going to pick whatever you want. Maybe you're not going to take hardly anything with you. Maybe you're only going to fly around your local airport. So you could probably leave almost all this out. So you could probably have your extras be down just a few pounds. You may not add a parachute to airplane. So you could probably leave this out if you're not going to bother with the parachute. And you might be a very light pilot. Maybe you're 150 pounds and you don't ever intend for anyone else to ever fly your airplane. So you could save some weight there. But if you have no idea what your gross weight's going to be, you don't really know how big a pilot you want to design for yet, you don't know how much baggage you want, I'd say go ahead and use something like this, 517 pounds. Or if you want to make it a little bit easier on yourself, use something like 510 or 520. One of the estimates that Raymer wants is the fuel fraction. So that's the portion of the fuel that's part of the gross weight at takeoff. And here's the equation that he uses, which is a kind of a complicated equation. And there are a number of things that he wants to know in order to do this estimate. And one of them is, how far do you want to fly? In other words, what do you want for the range of your airplane? He also wants to know what the fuel consumption of your motor is going to be. And he wants to know the prop efficiency. And most importantly, he wants to know the lift to drag ratio. Well, this doesn't help us a whole lot. We already know what the fuel fraction ratio is for our airplane. But another thing we can do is we can rearrange this equation and solve it for range and try to calculate what the range of our ultralight will be. So that's what I've done down here. So here's range in feet. Or this operation here is called a natural log. And here's going to be our fuel weight divided by our gross weight. This 0.975 is to account for the amount of fuel that you're going to burn while you're climbing. So that's where that comes from. Now, fuel consumption units up in here is pounds of fuel per second per brake horsepower. Now, Raymer does something a little bit confusing. He talks about some typical fuel consumptions for modern engines, but he uses slightly different units when he's talking about it. So he's saying that modern engines have from 0.4 to 0.6 pounds per hour, not seconds, per brake horsepower. So you have to be a little bit careful. And once again, fuel consumption, your prop efficiency, and lift to drag. Now let's talk about fuel consumption and your prop efficiency. Now I happen to have a Rotax 377, and I decided, well, let's do the fuel consumption for that engine. And so I thought, well, at 45 knots, we can probably run the engine at 55 RPM. And if you look at the graphs for that engine, that's a 2.8 gallons per hour fuel burn. And that's at 27.5 horsepower. So if we do the conversion on this, we have 2.8 gallons per hour times 6 pounds. Now that's pounds of fuel per gallon divided by this 2.75 horsepower. And that gives us a 0.61 pounds per hour per brake horsepower. And so you can see at 0.61, we're right at the top edge of what Raymer says that modern aircraft engines have for fuel burn. So if you don't know what engine you're going to use yet and you're interested in doing a range calculation and you're going to use a 2-cycle engine, I'd say go ahead and use this 0.61 for your fuel burn. And I think you'll be all right. But in order to stick it into the equation, you have to divide by 3,600. That converts hours to seconds. And I'll let you plug this in right here. Now let's talk about propeller efficiency. Now Raymer tells you to assume that your propeller efficiency, if you don't know what it is 0.75. That'll at least get you started. Now all the work that I've done seems to indicate at the propellers that we typically use on ultralights at the speeds we fly, I don't think we can normally get this amount of efficiency. What I've seen is closer to 0.5. So I'd say that for an ultralight, you'd probably be more accurate to stick a 0.5 in there for propeller efficiency. That's right here. But if you think your propeller is more efficient or you actually have actual numbers, go ahead and plug those in instead. So for the lift to drag ratio that I've got, and this fuel burn that I calculated here, and the fuel and gross weight calculation we just talked about, I came up with a range in miles, I converted from feet to miles, of 72 miles. I think that's probably not out of line. Now, you don't really need to do this if you're just flying around the local airport. There's really no need to know what your range is going to be. But since I'm intending this to be a touring airplane, I really would kind of like to know how much range I could have. Ways to make your range better then is to get a better lift to drag ratio, so increasing that lift to drag ratio, and that is what I hope to do by increasing my aspect ratio. So if I increase my aspect ratio from the current 4.1, I should be able to increase my range. Getting a more fuel efficient engine would increase my range, of course. So if I went from, let's say, the 377 to a 2-cylinder half BW engine, I would probably get down around a 1.8 gallon per hour fuel burn. And so that would extend my range quite a bit. And then, of course, getting a more efficient propeller would increase your range. And we're actually going to talk about that a little bit here in part 3. So that brings us to the end of Raymer's sizing calculations. So let's review what we've learned. So we came up with the coefficient of parasitic drag. We came up with this drag due to lift factor. We came up with lift to drag using those two values. And then we directly calculated the weight of our fuel, our empty weight, and our gross takeoff weight. Well, guys, I hope if you looked at part 2 and you looked here at part 2.1 that you found this to be much simpler and make more sense and not be quite as confusing. So let's talk about what's part 3. In part 3, we're going to work on engine sizing. And by sizing, they don't mean like the volume of it. It means the power, like the horsepower of it. And then in relation to that, we're also going to figure out what our prop diameter will be, the number of blades on the prop, and what will be the tip speed of the prop. Well, guys, part 3 should be out before too long. I've already made the slides for it, and it's going to be a fairly short video, so shouldn't take too long. Until then.